So, continuing my lecture series on nanocomposites, and we were talking about transition metal oxides. So, today I will talk about a very important metal oxide called titania, which is basically TiO2. And I will mainly focus on the photocatalytic aspect of titania today. And it is an excellent photocatalytic material, and it is mainly found to be efficient in UV light, although there are basically two phases of titania. One is called the anatase phase and one is called the dutyl phase. UV on irradiation of UV light, this titania becomes very much photoactive. Photoactivity is used to clean water, to decompose the impurities present in water, and it is very non-hazardous way of refining the water. Now what we need is that we need to use titania more in visible light. Although there are mixed phases of titania consisting of anatase and dutyl, which have shown some photocatalytic activity in visible light, still we would like to increase its application where we don't have to use any UV light. We can make the work possible by using visible light. So that is why people are doping titania with other materials. For example, they can dope titania with tungsten oxide, which makes a WO3 TiO2 composite, or they can make a composite out of niobium pentoxide and titania in B2O5 and TiO2. So we will call this one as TW and this one as TN. Now the titania which is presently available, it has got a lower band gap, and the commercial name of titania which is used is called Degussa P25, or in short TP25. It has got a band gap of about little more than 3. Right, and I will give you the value later on. It's a band gap little more than 3. Now for checking the photocatalytic activity or the photodegradation, we use methylene blue. This is an organic material. What should be the properties of an efficient photocatalysis material? So an efficient photocatalysis, PHC, it should have photon harvesting. It means it should absorb the photon. Then the generation of carriers should be very swift, electron and hole pairs, and they should be separated. They shouldn't combine. So these are the main two properties that an efficient photocatalyst have. Main is this one, the generation and separation of the electron and hole. This is the main thing that we will focus upon. Now, as TiO2 has a band gap which is comparatively, you can call it a large compared to other semiconductors. Now, that is why due to this large band gap, there is a higher recombination. So let me put it this way, use a different color here. It's got a comparatively high band gap, and this is causing what? This is leading to a higher concentration, recombination of the carriers. As I've told you, this electron and hole pair, there should be the less is the recombination, the better is the photocatalysis. So these high band gap will cause a higher recombination rate of these photocatalytic carriers, and also they have got a low surface area. So we need to work on these two to make it more efficient. Now what happens when we add tungsten to it, or WO3 to it? So when WO3 is added in TiO2, now this W, which is in 6 oxidation state, this what will do, it will migrate to the surface. It usually has a tendency to migrate to the surface of the TiO2. And it will this will cause a decrease in the recombination of electron hole pairs. Now, as it goes to the surface, it will attract more. It will have the capacity. So the free ions, or the higher oxidation state ions, are at, if they are at the surface, so they will be able to photo degrade the methylene blue much more, right? And also due to this tungsten, there is decrease in the recombination rate. So, and first of all, the band gap lowers down, and there is a decrease in recombination rate. So basically 3 things happen. Firstly, it migrates to the surface to accelerate the photocatalytic reaction. There is a decrease in band gap, right? So more number of carrier generation will take place, and there is a decrease in recombination of the electron and hole pairs. Now what about this other material, niobium pentoxide? This niobium pentoxide, it is basically an N-type semiconductor, which are having a band gap of about 3.2 electron volts. Okay, and also like TiO2, it has got good chemical stability and non-toxicity. Chemical stability is good, non-toxic. These are the 2 qualities which makes it applicable in as a composite material. Now we actually prepared this TiO2. I mean the composite of titania and tungsten oxide and titanium and niobium pentoxide by sol-gel route, and we did some optical studies like UV-vis spectroscopy showed a plot like this. The reflectance percentage was plotted here. So it showed a plot for, this was for DP25, the pristine material. Then a similar trend was followed by tungsten oxide. However, for tungsten nitride it showed a decrease, and this took place around 400 nanometers. Now, since addition of niobium pentoxide to titania is reducing the absorption peak, so and it is also taking place at a wavelength which is between the visible region 400 to 700. It implies that this composite is more active in the UV region compared to the visible region. Now, on calculating the band gap by Kuvelka-Monk equation, it says that the absorption coefficient is equal to and where alpha is the absorption coefficient. It's a different color here. Alpha is the absorption coefficient, R is the reflectance, A is a constant, and the interesting thing is this value n. Now n is equal to 1 by 2 if it is a direct transition, and if it is equal to 2, so it means it's an indirect transition. Okay. Now in case of TiO2, this n is an indirect transition, so it has been taken as 2. Now this plot of Fr h mu whole square it was plotted with h mu electron volt, and this is basically electron volt square. So we obtained different plots for different compounds. For titanium nitride, for Tn it was like this. For the pristine dp25 it was this one, and for titanium tungsten it was like this. So this stands for Tw, which has got the lowest band gap. This is for Tn, and this is for dp25. You can see that in so addition of or making this composite had lowered the band gap both with respect to Nv2O5 and with respect to titanium tungsten titanium composite. Now the photocatalytic activity was again determined by Langmuir-Hessenberg equation. So let me write it down. It was again derived from absorbance studies. And it says that C by C0, very well known equation, is equal to K F to T, where T is the time, C0 is the initial concentration, C is the concentration, this is the rate constant. This value is the rate content. So it tells how well the process is going on. And for the three types of materials, we plotted ln C by C0 with respect to time, which was in minutes. We obtained the highest activity was shown by titania, whereas titania, with respect when it was made a composite with tungsten, whereas the addition of niobium pentoxide caused not a very encouraging picture. So it caused a lowering of the rate, and this is without any doping. So you can see that since the composite made up of niobium and titania, they act mainly in the UV region, so their efficiency is very less, very poor compared to this composite made out of titania and tungsten. Okay, now some of the we can put it like this: K TW is greater than K dp25, which is again greater than K Tn. Now this enhancement of photocatalytic activity by using titania is due to formation of photogenerated carriers, and as we have already told you that the titania ions, they move to the surface and make the reaction faster, and the crystallite size obtained from XRD was also found to be smaller when we are making a composite, and this was smaller both in the case of the two composites. But since this is more active in the UV region, so no enhancement of photocatalytic activity is observed, whereas in titania the lowering of crystallite size actually caused the increased photocatalytic activity. We can correlate with that, and the band gap for TW is 3.02 electron volt, whereas for dp25 it is 3.08, as a little more than 3, and whereas for titanium nitride, titania NV205 nano composite, it is much higher. dp25 is 3.22, and for titania and NV205 composite, it is 3.08, the lowest of the not the lowest, but it is still less than this dp25. So even if this Tn is satisfying all the properties to enhance the rate of the reactions, it is not showing an increased rate, mainly because of the fact that it is more active in the UV region.